So we talk about computing mobile polytopes with some applications in both computer science and also quantum information. And I first wanted to ask if are there also quantum people here today? I think maybe, yeah, okay. So thanks for coming. So I think it will be nice. I added some quantum slides in between, and I think it should be accessible to all, and I think it will be fun. So this is joint work together with Matthias Kristanov, Vladimir Liskov, Helmut Boer, Michael Walter, and Jeroen Zuidam. This was also at Stock 2020.
Okay, now you've made events. They're classical now.
Oh, they're classical now. Yeah. Very good. So and as if there's questions at any time, please feel free to interrupt me, and then I can. Okay, so first I want to do a little introduction, but placing all this stuff in context. So it might be a little bit abstract, but after that I'll make things more concrete, and we'll see how it goes. So what we're looking at are tensors. So tensors are taken here on three factors: C, A, tensor C, B, tensor C, C. And tensors can be many things. So they can describe algorithmic problems, most notably matrix multiplication algorithms. They can describe quantum states. And also they can describe combinatorial problems. For example, CAPSAT, but also many others. And we really, when talking about tensors, the thing that we really want to understand is relations between different tensors. So let's say I have two tensors, T and S. I want to ask when it's possible to apply matrices to the three factors. So here A, B, and C, which are on the corresponding side, so that I can apply it. Then I can obtain S from T, and this is something called restriction. This is just an example of such relations. So you have other ones, also asymptotic versions of these things. This is really what we want to understand. But these structures are very intricate, and they require really rich information to really say something about it. And that's what we want to understand. And a moment polytope is just rich information like this. It contains such rich information of both a geometric type and a asymptotic representation theoretic type. I will not talk about representation theory in this talk, but just like, all right, just know that it's in the background. Some context. So why do we care about polytopes? So they contain nice information, but what do we actually do with them? And they're relevant in a couple of areas. So the first I want to name is geometric complexity theory, where they have been proposed as potential obstructions when studying matrix multiplication complexity. And they just really read as like lower bounds. So this was in Stock 2011. In quantum information theory, so these mobile polytopes are also called entanglement polytopes, and they're really a very natural way to give some entanglement measures to your quantum states in terms of the quantum marginals that it can reach. And this was in a science paper from 2013. Also, these mobile polytopes are specifically relevant in something in Stassen's duality theory. So this is a dual theory to something called asymptotic rank to construct certain functions called quantum functionals. I will talk a little bit more about them later, but this is really in the study of this asymptotic rank. I will not define it, but this conjecture is something that's seen like a lot of recent attention. So people care about this, and the mobile polytopes are really like central in a specific construction there. So this is from 2018. These mobile polytopes also show up. So these are mobile polytopes of tensors. You can also actually define mobile polytopes more generally, and then they show up in the setting of non-commutative optimization. I also won't talk too much about it, but it's really an important application. So this was from Fox 2019. So what do we want to do? So these mobile polytopes are really important in many different fields, but actually we know very little about them. So they're polytopes. So you could write them down just as a bunch of vertices, but we actually almost never know them. So we knew only in very small dimensions what these look like. So this would be C2, then C2, then C2, and the same with them with extra C2 factor. This was from this science paper that I mentioned previously. So really small dimensions and some sporadic examples. And really, we want to know concrete properties about these polytopes, and they can really lead to improvements across these disciplines, all the things that I mentioned before. So for example, it's been stated as specifically an open problem to understand these mobile polytopes of matrix multiplication and unit tensors, which was in this 2011 paper, but really since 2011, no progress on this problem has been made. Like we didn't really know anything. And so the general framework of our work here is that we want to obtain new examples, and they will be an important step to really understand these polytopes better and get new concrete theoretical results, also in bigger dimensions than just what we're computing. So what did we do? Well, we have a new algorithm to compute these things, and it's really geared towards practical computation of these polytopes. And practical, it doesn't really mean efficient, so it won't be possible to find efficient algorithms, because in some cases the amount of vertices of these polytopes, they will already be exponentially many. So it's really not efficient. That might not be possible, but really practical is to just get as many examples as possible is really the goal. And what do we do? So we have this algorithm, and then we're able to determine all moment polytope tensors in C3 tensor C3 tensor C3, and also in C4 tensor C4 tensor C4, but only probabilistically with some probability of success. And this is really an order of magnitude larger than what was done before. And then we already implement this the general idea that I mentioned on the previous slide. These examples then inspired new theoretical results. So we are able to find separations between these matrix multiplication and unit tensors, the moment polytopes. We found some no-go results. It's some operational with moments related to acidic restriction. I'll talk a little bit more about this later. And also a last one thing, which is was maybe a bit more surprising because it's not directly related to moment polytopes, is something about non-free tensors. I'll talk about it if I have free time, but if I don't have time, I don't think it's okay. Okay, so this was a bit abstract introduction. So now I want to talk about what actually are moment polytopes, and then our algorithm, and then I will talk more about these applications. So what are moment polytopes? So I will give you the most hands-on definition that I know. So there's actually multiple ways to define these things. I want to do it now as follows. So I have this tensor, it has 3 factors. So I can think of it as just a block of numbers, a 3-digit grid of numbers, size A, B, C. And then I want to do the following to it. So I want to take this tensor and I can flatten it to a matrix. I can do this in 3 ways. And what I just do, I take my block of numbers and I just take the slices and put them next to each other. So I get a matrix that is size A by B, C in this case. And I now take this matrix and multiply it with its own conjugate transpose to get an A by A symmetric positive semi-definite matrix. And then I want to look at the eigenvalues of this matrix. So this is R1T, and I want to sort them from big to small. So these are the eigenvalues from big to small. And I want to normalize them so that the sum is 1. So that is what this R1 here does. Okay, well, I can do this in 3 ways, because there's 3 ways that I can group the factors in this case. And this will give me some vector in RA times RB times RC. Well, I don't want to do this just of the tensor T itself. I want to do it of some other tensors, T prime. And I want to look at all T prime that I can obtain by doing these restrictions that I mentioned before. So apply matrix A, B, and C to T, like all tensors I can obtain here. But here, approximately, so if there's 3D lines here, so what does that mean? That means that, in fact, if I look at, so it means that I can get arbitrarily close to T prime. So I can look at all restrictions of T, this will be some set, and then I can take the Euclidean closure, and I want T prime to be in there. Okay, and this is what the moment polytope of T is. Yes, so there's other descriptions, and at this point, I want to do a little quantum interlude. So for the non-quantum people, it won't take long, don't worry. I just want to quickly say what the interpretation in the quantum setting is. So let's do it. So in the quantum setting, these tensors T, they are quantum states. And often, so quantum states, we need to normalize them. So I take my T and I just normalize them. This won't change the definition of this polytope. And what is this? So there's a multiplier of quantum states. So I have these 3 systems here, and I can think of like, let's say 3 parties, Alice, Bob, and Charlie. They share some multiplied quantum state. And then these ABC operations that I do here, they have a physical interpretation as LOCC operations. So these are LOCC operations, so stochastic, local operation classical communication, but with stochastic added. Which basically saying I can do local operations, local unitaries, classical communication, and using these operations, I can get arbitrary close from my states T to T prime. That's what this means. So in some sense, it's a very weak notion, but sometimes we can show that this is not possible, which would then be a very strong statement. That makes sense. So yeah, so these are operations that intuitively they cannot increase entanglement in the system. And then what are these R1 things? Those are exactly, so let's say I write T prime as a state psi. I look at the density matrix of the state. Then I can look at the reduced density matrix, let's say at Alice, and I can look at the spectrum, so the reduced spectra of this thing. And that will be equal to this thing. So what we have here, we're basically rewriting the reduced spectra of the states I can reach using SLS operations. And because the spectra, they characterize the marginals reachable, this polytope characterizes like all the marginal density matrices, all these three systems that I can reach on the SLS. And this is why they also have the name entanglement polytope. Yeah. Okay, so back to the general things. So the main theorem, which I think is surprising and very cool, is actually that the set that I defined. So I didn't say this before, but it was totally not clear that this was a polytope. Like not clear at all. But it turns out that it is. Which is very surprising. Like what we have here, we're doing very nonlinear things. So we're doing ABC with identity, it's very nonlinear, taking eigenvalues, all nonlinear operations. And somehow what we get is a set that is defined by a finite set of linear inequalities. Yeah, so this theorem has a long history. So it's based on work of subplexity theory, event theory, representation theory. Yeah, this was kind of the basis for why these objects are like cool and nice to look at. Yeah, so I have some examples. So I have two tensors here. So this is in C2, tensor C2, tensor C2. Here I have the unit tensor. So the constant people who know this as the THZ states. Here I have the W tensor, which constant people know as the W states. And here are the polytopes. So I write them here as just the vertices. And then the polytope is the convex hull of these vertices. And also you read this, so we have three systems. So this system first, that will be these two columns. This system will be these two columns. This will be these two columns. And I can in this case make nice pictures because we know that each of these in the columns, this needs to sum to 1. So I might as well only plot the largest one, and then I get a three-dimensional picture, and I can put it here. And what we see is that the unit tensor actually has a bigger polytope than the W tensor. So the W state, it can really not reach as many. So in the quantum setting, it cannot reach as many marginal systems, and it's cut off by this one linear inequality. Yeah, okay, so that was one example. So now I want to move on to how our algorithm works. Are there any questions so far? Seems like
You said the first one had the THZ state.
Yes.
And the second one is the
W state, yes. Yeah. Okay. So let's talk about how we compute them. So our algorithm is based on a description of the moment polytopes, which is due to Franz, which I now want to explain. So I will be explaining a different way to write down this polytope. And for this, I need to define some things. So first, I want to define the support. The support of the tensor is it's the indices where it is non-zero. But then I don't write them just as the indices, I write the indices as the standard basis factors. So I have a little example here of the W state. So this was this tensor. So what is the support? So when it's at non-zero, it's at index 1, 1, 2. And then I write them as the first standard basis factor, second standard basis factor. And then I do this for all the items in the support. And then I get this set. So this lives in RA times RB times RC, just where our moment polytope lives as well. Okay, I want to define something else, which is with something called dominant vectors. They're just the vectors in Rn that are sorted from big to small. And then I want to do this on the three systems that I'm looking at. So that would be dA, dB, dC. Okay, and now I want to define, given Franz the characterization of the moment polytope. So what I'm going to do, I'm going to take my tensor T, and then we're going to apply some restriction to it, so matrix A, B, and C. And then I'm going to look at the support of this tensor and take the convex hull of it. So this will be some polytope based on the support. And now what I want to do, I want to take ABC to specifically be lower triangular matrices, and then take the intersection of all convex hulls of supports I can reach using lower triangular matrices. And then I don't want to and then finally I want to intersect with these dominant vectors. So the moment polytopes, they live inside this set D because the things are sorted. So that's why I want to take this intersection here. And then one final thing I need to do, I don't need to look just at t. I actually need to take some random point in the, so what we call the orbit of t. So I want to apply some random matrix ABC to it, just do some randomization to start with, and then start with this t prime. And then for generic, for generic A, B, and C with the heads here, I will get the following equality, which is at the moment polytope is actually equal to this weird intersection that I was just defining. Yeah, so this turns out to be true. It's very surprising. Like, I mean, this I don't think this looks a lot like what we were looking at before, but yeah, this turns out to be true. Very, very neat, I think. And this is really what the argument is based on. So are there any questions about this thing so far? Then I'll continue. Oh yeah, so I already said it, so we can take it randomly, and that will be good. Okay, so let's try to use this to compute what the moment polytopes are. So one thing that we could try. So this support here, this is always a subset of some finite set of possible supports, because there's only a finite number of indices of our tensor. So in fact, the terms here is only one of finitely many. So one thing you could try is just to go through all terms and see if you can actually reach that support using lower triangular matrices. So I have this task here. So let's say I have a support. I want to determine whether there exists lower triangular A, B, and C such that I can go get inside that support. So that's just some task. And this we can do using something called Berg basis. So basically what we want to do is this is just solving a linear, solving a polynomial system. So I can look at the supports that are outside S. Those I want to be equal to 0, which is this following. These things I want to be equal to 0. And if I take my A, B, and C to be symbolic, lower triangular matrices, this becomes a polynomial system. And I want to solve this. So asking whether it's simultaneously 0. And this is something that you can do with growth basis. So if you don't need to know what growth, this is a way to that you can show arguments for this exists. Okay, so this will give you maybe an attempt and an argument. So what you could try to do is to loop over all possible supports and run this above task. And then just take everything that you keep, take the intersection. This will give the result that you want. So that is what we tried at first. So we take a tensor C3, 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 and we try this with a couple of extra smart things. And then we run an algorithm. It runs for like 20 hours on Snellius, which is just a national supercomputer. And then it's ran out of memory. So it really wasn't working well. It took way too long. Out of memory was actually due to a bug in the program that we were using, which we were not able to fix. But in any case, this was not really working. And it turned out, I said, so it didn't terminate for 20 hours, and then at some point it ran out of memory. Okay, so what is the main idea? Is that instead of looking at the supports, it's better to look at the possible inequalities that you can get. So you have a finite set of polytopes here. They have only a finite set of possible inequalities. And those we can try to figure out if are true or not. So it's the following lemma, so I have it in formula here. So it turns out that this polytope can be defined using some inequalities H, but each satisfies some things. So I have a little very cartoonish picture of our A plus B plus C here. So this dots here you should think of as possible support. So just as these basis vectors indexed by these possible indices. And what would inequality be? That would be so inequality would just be a line. So this was just two-dimensional, but this would be larger dimensional. And then you can look at this like one side of the inequality. So this is what it would look like. And what this properties have, so this first property is that this H should be tied on precisely A plus B plus C minus 3 elements of this set of supports. So here that it goes through here exactly, that means that it's tied. There should be exactly A plus B plus C minus 3 elements on this hyperplane. And the second thing is that we can actually bring the support of T using its lower triangular matrices. We can bring it inside the set SH, which basically means that we can bring it to one side of the inequality. So we can take, so we can bring the support inside the elements here that is all lying on one side of the hyperplane here. Okay, and based on these two things, what can an algorithm be? So what can we do? We can actually enumerate all H's that satisfy this property 1, which is only a finite set. And then we can filter the H that satisfy the second property. And this is exactly this task that I showed before using this coordinate basis. And then putting this together, you get a list of inequalities that define your polytope. And this seems to work very well. So now we can do tensors using algorithm in C3, C3, C3 in just seconds. So that's really good. Okay, so then we might ask, what about C4, C4, C4? So 3, 3, 3 is now easy, so can we do 4, 4, 4? Well, there's many bottlenecks. So all these things are still very exponential in the input. So it wasn't immediately possible, but we put many optimizations. So these are really these practical considerations that I mentioned previously. So I have here a list, and maybe maybe I will skip what we did exactly. But for example, if these coordinate bases, you can do them instead of with prime fields, instead of over the complex numbers, or over the rationals actually that we did originally, and some other optimizations. Okay, and then we turned out that we can do it. Okay.
How long did that take?
How long? That's a good question. So now it's really dependent on what tensor you do exactly, but all of them I've tried would be able to do like 20 minutes. So there's two parts, so maybe I'll go there. So there's two parts. So the first one is enumerating all the H. That takes like 5 to 10 minutes, I believe. And then computing the polytope for specific tensors, that can take up to 20 minutes. But for major applications I get to later as well, it's only like 5 minutes. So it's really it's
And it is on supercomputer as well? Or?
No, I forgot to say. But this algorithm just runs on my laptop.
Okay.
Yeah, so yeah. After the seconds, it's just on my laptop. Yes.
Even with the previous approach, you use global basis, but you only need to like satisfiability of the system, and you don't need to find a solution.
Yeah, correct.
So you can get like an exponential speed. Like you don't need global basis, right?
So what I know, and I would love to, if you have more ideas of what you could do. So the only other way I know is to do like homotopy continuation of methods.
Or yeah, like you can use numeric methods, or even symbolically, it's like faster. It's like satisfiability and stuff.
Yeah, then I would love actually to talk to you because I tried to find this, and I. So basically, we just do the whole problem basis now. We also try this homotopy continuation like numeric methods, but those have like a bigger overhead per computation. And that's actually made it slower because we're running like a lot of coordinate-based computations. Yeah. Okay, more questions about the algorithm? Then I'll continue to the applications. So the first application is that we now actually know all moment polytopes in C3, tensor C3, tensor C3. There's exactly, okay, there's 29 ones up to permutations of the systems, but 29 really unique ones. We know them for certain. So the way that why this is possible is because there's a classification of the orbits of tensors in this format, which is due to Numi and Popov. And then we can use our algorithm to compute these moment polytopes. And we also need to do some manual work. So in this classification, there's also some continuous parameter families of tensors. And those we need to do by hand to deal with these parameters. And lastly, so we need to do some de-randomization. So I mentioned previously that the algorithm or this Friend's description, it uses first that you need to randomize your tensor to actually get the full polytope. But in this case, we can do some smart simple techniques to really de-randomize the results and to have for certain that these are the polytopes that we want. Okay. And now I want to talk about the other results. And for this, I want to do a little bit of an intermission with some backgrounds, about these quantum functionals that I mentioned before. So I just wanted to define what these are. I think they're very nice objects. So what are the quantum functionals? So first I want to take a probability distribution on three things. So theta 1, theta 3 is a probability distribution. And then I want to, for each of these thetas, I want to define a different quantum functional f theta. And what I just do is that I take the points for my moment polytope, and I want to evaluate their entropy. So these points, they are probability distributions, they have some entropy. I can evaluate this, some standard entropy. for all the points, and then I can take the weighted average of the of the tree, and then take everything 2 to the power that value. And this is a function that I can define. So yeah, it's just nice. I can do this, but this one actually has very nice properties. It's said by the following. So I'll say here. So what does it satisfy? So they satisfy that they're additive. So that means that whenever I take 2 times t and I take this direct sum, which basically is just saying I have my block of numbers, my other block of numbers, I just put them joined at the corner to get a new tensor. Then this one will just so we'll just get the sum of the function you started with. And the second one is when you take the tensor product of two tensors, and then you just get the product of the these quantum functionals. And lastly, and the first two is that they are monotone. So this means that whenever I take t and I apply some matrix A, B, C to it, I will always actually get a lower value. So they are also in the quantum context, they're really like strong entanglement monotones. And lastly, they are normalized. So this is that whenever I choose the product tensor, I should get 1. Okay, so why is this nice? So there's actually a theorem, and I will say it very informally here, which says, it's by Strassen, which says that this asymptotic rank is actually equal to the maximal value I can get when applying functions f to my tensor t, where I take f to be inside this set x, which I define precisely as the set of functions that satisfy these 4 properties. So the set of functions that map from tensors to the real numbers that satisfy these properties, I take all of them and evaluate the maximum I get as an asymptotic rank. And this is, it's a bit abstract theorem, but it's very nice. So if you know the asymptotic rank, in particular, you can determine the matrix multiplication exponent just by looking at the asymptotic rank of the. So this will be the matrix multiplication tensor, but just of 2 by 2 matrix multiplication. So this is a very small tensor. So maybe I'll quickly define what this is. So this I mentioned them many times before. This matrix multiplication tensor. So they're defined just basically as a recipe for how to multiply matrices. Which is the following tensor. So it's just defined as this one. So they characterize matrix multiplication. And just looking at the small one, a 4 by 4 by 4 tensor, you would get the asymptotic rank. And it turns out that these quantum functionals, they are inside the spectrum by these properties. We just don't know if they are all. And they were actually the first like non-trivial things that were found in this spectrum. So, and the nice thing also, so these are called the quantum functionals because they're really inspired by quantum information techniques to look at them. And it's really like quantum information techniques that influence this very algebraic complexity theory result, which I think is also very nice. Okay, so that's just a bit of background. So the point is, we care about this matrix multiplication and we care about the moment polytopes by the quantum functionals. So, and I forgot to mention, so this set X is also called the asymptotic spectrum. So this is like Strassen's theory of asymptotic spectra. Okay, so what did we find? So our actually found that this matrix multiplication tensor of this 2 by 2 matrices did not contain a point, namely this point. So I have a half, 3 times 1/3, 4 times 1/4. While this unit tensor, or so for quantum people, this would be like a tiered set of order 4, did in fact contain it. So this polytope is strictly smaller than this one. Or it's so in this case this is strictly smaller. And this actually inspired us to come up with the following theorem, which is general, and that is that we found a point PC for some values of C that does not lie in the polytopes of matrix multiplication, but it does lie in this unit tensor thing here. And what's this point? It's basically this point here. So I have this U2, which is just the uniform probability distribution on m things. So here it's 1/2, 1/2, and then here instead of 3 you get C minus 1, and 4 you get C. So a little bit about the quantum interpretation of this result. So what does this mean? So this matrix multiplication tensor is actually also a very natural object in quantum information theory. Namely, it's equal to when you have 3 systems, and each of the systems, they share one maximally entangled state. So the NM2 would be, they have 3 parties, and each they share an EPR pair each. And then this state here, I already mentioned it, this would just be the G at Z state of order C. And basically what this result is saying is that the expressivity of this state, you can reach less marginals than you can with this G at Z state. And we're actually able to extend it also to matrix product state. So the extension is then as follows. It's just that instead of 3 parties, you just have more parties, and they each share EPR pairs in a line, like maximally entangled states of order n. And here G at Z state is also extended that there's have some big entanglement with all of them. And this is actually the first result of like limitations of these kind of systems. So really, if you have this state, you really can do more with it, which I think is a very interesting thing also in quantum information. Okay, then one more final remark about this. So this theorem actually is also interesting by itself, the way that we do it. So we relate this matrix multiplication polytope in a very nice way to something called polynomial multiplication tensors, which I will not define, but if you know what this means, it's quite nice. Okay. Yes. So the next thing is about this asymptotic restriction. So first I want to define it, but first an observation. So I already talked about restriction before, so I can go from T to S. So this is some notation just saying that you can take 3 matrices and go from T to S. That's this called restriction. And this implies that the moment polytope of S has to be contained inside the moment polytope of T. And this is very easy to see from the definition because we are looking at all possible things we can reach from T, and then you can just go from T to all things you can reach from S. It's like a transitive relation, so that's why you get this this thing easily. Okay, then I want to define something called asymptotic restriction. So asymptotic restriction, what is this? So I define it with this tilde here. And what does this mean? It means that I might not be able to go from T to S immediately, but if I have many copies of it, so that would be taking lots tens of power here, lots for the power, then I can go from S, and here I allow some slack. So this is little O of n, so as n goes to infinity, this will become arbitrarily small, and then I'm really going from T to S asymptotically. This is called asymptotic restriction. And a very natural thing to ask is, well, if you have an asymptotic restriction from T to S, do you then also get this moment polytope inclusion? So we saw that this moment polytope really has some asymptotic information, also by these quantum functionals that I mentioned before. Also due to something that I did not say, but the representation theoretic definition of the characterization of the moment polytope also have some asymptotic qualities. So this is really like a natural question to ask. And it turns out that this is not true because we found the counterexample. This counterexample, I can give it to you. So I again look at this unit tensor, so in this case S of n squared. And it's actually known that there is an asymptotic restriction from the matrix multiplication tensor to S. So this is that was known before. But by the previous result, we actually found that so this one is not contained in the matrix multiplication, just because it doesn't have this point that I mentioned on the previous slide. So that proves that this cannot be true. Okay, so why is this? So I already mentioned why it's interesting, but I have a bit more why it's interesting. So by this same theorem that's Stassen that I put on the previous slide, you actually have something stronger. Yeah, so it doesn't look stronger, but it's something that's actually stronger than what I put on the previous slide, which is that having asymptotic restrictions from T to S is actually equivalent to all functions from this asymptotic spectrum to be monotone. So I just take all functions from the asymptotic spectrum and I find, well, they're all smaller, like applied to T, applied to S, they're all smaller than applied to T. This then applies that as an asymptotic restriction. So this in itself is a very nice theorem. So this is also the motivation. And basically, what does this mean? So these quantum functionals, so this thing is not true when you replace this smaller equal to by moment polytope inclusion. That's basically what this is saying. Because you don't have implication one way. So these quantum functionals, they really pick out some special information of these moment polytopes, which is this gives some more operational meaning to what these moment polytopes are, which is what's interesting. Okay. I think I'm doing very well on time. Are there any questions so far? Then I'll continue to our lesson thought. So this one is a little bit maybe different in flavor, but it is related to what we're doing. So this should say, this is an error, sorry, this should say non-free tensor. So, okay, I want to define what a free tensor is. So the definition is not too difficult. So maybe forget about this part first, just look at the tensor has free support whenever I have my block of numbers and I look at a line through it in any of the three directions, just any line. And when I look at this line, I only find one non-zero element. That means that it has free support. So what do I write here? I see that whenever an element is non-zero, that means that all other elements in that line, so I vary here only one coordinate, they should be equal to 0. So it's a very like sparsity condition on your tensor. So that's what it means to have free support. And the tensor is free if I can do basic transformations ABC, which are irreducible, to go from tensor T to T prime that has this property, this free support property. Okay, that's the thing. So some motivation. So these free tensors actually play a role in this theory of asymptotic spectra that I've been talking about a lot. I won't explain how exactly, but we care about them there. And yeah, so one first thing to note is that most tensors are not free. And this you can just find by a dimension counting argument, because the free support means that it's super sparse. And then all three tensors that you get are just in the orbit of T. So you can do dimension counts. Well, how many variables do I have here? This is A squared, B squared, C squared. That means that I can bound the dimension by putting those two together. Even though the dimension of the whole tensor space will be larger, and it will grow like A times B times C, which will be bigger. And so for large dimensions, most tensors are not free, but we actually knew no examples of this. So there were no explicit examples of these non-free tensors. This is something that occurs more often. Like there's a property that most things satisfy, but we actually cannot find explicit examples. Like the same is true in like TensorX settings and stuff like this. But I won't talk about that more. So what did we do? So we found first the theorem, which basically says that whenever you have a free tensor, you can also look at the tensor in this orbit here, the orbit closure, I think, with the norm of these eigenvalues minimal. So somehow this point here is like I have this mobile polytope. I can look at the norm. This is like the minimal norm point that you can get. That's what this value is. And if you have something like this, then S actually will have free support under a unitary exchange. So not just ABC invertible, but actually unitary. And we'll use it in the contrapositive to find a non-free tensor. So we'll find what we do. We find we have the T, and then we find the S that satisfies its properties, and then we show that it does not have free support over unitary base chains, which would then imply that T is not free. And we did this, and we find some very nice tensors that satisfy this property. So the following tensors in Cn, tensor C, and tensor N are not free. These are really inspired by the results we got from our algorithm. Like to do this comparison with these moment polytopes, you need to know what a moment polytope looks like. So that's really where this came from. And what is the structure here? So basically what I do, I go from these rows. In the first row, I put all ones except at the last entry. Then I go one up and I put a 1. Then I go to the next block. I go take the same amount, but now I put the 1 in the left position. I put here the 1, and now I put the 1 left here. So maybe this one will give a better thing. So here I have 3 ones, 1 here, 1 here, 1 here, and then in the corners I have these ones. So it's the structure. And you will notice that it's super sparse. It's like almost free. Like where it's not free is in this row over here, in this direction. So I should have said, so the way I write this tensor, so these are like the slices, right? So this is like the first part, and then I put them back to back. And really only in this first direction here, you have this non-freeness. So this is like very surprising. So it's not free, and it's actually very, very sparse. Okay, I think I'm about through my slides. So yeah, so one thing that I wanted to say is that the algorithm is actually very general. So it works for any representation of any reductive group for people who assess this. So basically, if you have a nice group in representation, we can run an algorithm and compute moment polytopes. And this is really relevant for this non-commutative optimization setting where you actually care about these different representations. Yeah, so reductive group, it just means that the group is nice. So if you just know like a general linear group, orthogonal group, subtractive group, and products between them, that they all work. Okay, and I want to say that the technical version of this paper will be archived in 3 parts. So we have this paper about computer monopoles, we're actually not on archive yet, and hopefully soon. These are the 2 applications that I mentioned. So about this matrix multiplication is done next one, and about these non-free tensors. And I also wanted to say that this paper will also actually give an accessible introduction to the theory. So this monopole theory, it's all very, I would say, general when people like in the literature, everything is super general, and I think very hard to read if you come from computer science or for quantum information theory. So we really give an accessible introduction specifically for tensors, which I hope will be like very nice for people to read when it's out. And that's it. So yeah, thanks a lot. Yeah, so any questions?
So if you go back
Mhm.
to like the quantum functionals and the there.
That's the restriction?
Yeah.
Yeah.
So here is Strasser proved this before defining the quantum function. Like
Yes. Yes. He knew only 3 specific elements of this spectrum, which were the flattening rates, which is doing this flattening as I said before, and just looking at the rank of the matrix that satisfies these properties. And he didn't know anything else. He looked at some special cases. So this would be like the asymptotic spectrum of just all tensors, but you can look at like subset of tensors. I'm not sure if you heard of like oblique tensors and stuff like this. Maybe we can talk about it more later. And then he did find some more points. And that also relates to this freeness, but maybe I won't say too much about it now. Yeah. Any other questions?
we don't have questions.
Yeah,
Thank
then
you.
okay.